Good morning, students. Today, day 29, and we want to finish today wave optics. Okay. So, in wave optics that we started yesterday, we studied about interference. Okay, two sources. What are the wave equation, amplitude, frequency, everything. We are already knowing because we studied waves already. Okay. And interference also we saw yesterday. How to calculate the resultant amplitude when the two waves are interfering, how to calculate the intensities of two waves which are interfering, what is constructive interference, what is destructive interference, what is called maximum intensity, what is called minimum intensity, what is the ratio. Okay, today what we are starting with, now suppose that two sources are having same intensity, I, okay, and there is phase difference between the two at the meeting point, which is phi. Then what was the resultant intensity? What we discussed? It is actually I1 plus I2 plus 2 root over I1 into I2 into cos phi. We did question also on this yesterday. Okay. But now this is 2I plus 2I cos phi. 2I plus 2I cos phi. Now take 2I common. This is 1 plus cos phi. Okay, and this 1 plus cos phi we can write as 2 cos square phi by 2. 1 plus cos phi we can write as 2 cos square phi by 2. That means this becomes 4I cos square phi by 2. When two sources are there, which is intensity is I, their maximum intensity used to be 4I. We can see that for maximum intensity, what should be the phi value? 0. For maximum intensity, phi value should be 0. If you put 0 over here, what will be coming resultant intensity? 4I. That is the maximum intensity. So this value we can write as I max into cos square phi by 2. Now sometimes this question comes directly. Okay. So that's why I told you this. Right? So this is the resultant intensity. If the two sources are of the same intensity, then we are going to get it as I max into cos square phi by 2. Okay. Yesterday we did question on this one. We want to have one more question on this one, we will do it. Okay. Now suppose here itself we will do. Suppose we have two sources. Okay. Intensity of both is I and I. And suppose they are meeting at a particular point, and at that particular point resultant intensity is also I. Okay. Then what is the phase difference or what is the path difference at the point where they are interfering? That is somewhere they are interfering here. Okay. Like this. So here also resultant intensity I am saying is how much? I only. What you will do? IR equal to I max. I max means 4I into cos square phi by 2. Okay, here is I. So I equal to 4I cos square phi by 2. I and I gets cancelled. This is 1 by 4 cos square phi by 2. Okay, taking square root both sides. 1 by 2 equal to cos phi by 2. Now, cos inverse 1 by 2 means what? 60 degrees. Okay, so 60 degree will come over here. So 60 degree equal to phi by 2. That means phi is how much? 20 degrees. We got phi value or phase difference. Now, you want path difference. So, we know that what is the relation between phase difference and path difference. Path difference is, or rather phase difference is 2 pi by lambda into delta x. This is what we write as phase difference, right? And that's equal to 120 degrees. So 120 degrees in terms of radian, what we can write? What we can write? 2 pi by 3. 2 pi by 3. 2 pi and 2 pi gets cancelled. Delta x comes out to be lambda by 2. Okay. So in last class also we did similar question. Okay, but that we solved from here. Okay. Today we have done two more steps and we got this formula. And this question we solved with that formula itself. Okay. Alright. So this is how it is. Why we did it? Because this directly is asked in the question. Okay. Now what? Now we are going to see Young's double slit experiment. This is the main thing about this chapter that we have. Okay. That means how to see that interference pattern that is given by Young's double slit experiment. So what he did is he produced two sources, and those two sources waves are going to interfere on a screen. How he produced two sources? That is from single source. And the reason for that is because it's impossible to get two coherent sources. Coherent sources means what? Same frequency sources. Okay, which will have the same phase difference at all the points. Those phase difference is not going to change. Okay, and in this case, phase difference depends on path difference alone. Phase difference between two waves interfering at any point, sorry, interfering at any point depends on path difference alone. That means phase difference at any point remain constant. At any point remain constant. Now why it's happening? Because we have taken coherent sources. And the interference such in this way, whatever interference we are getting, that is called sustained interference. That means for a longer period of time it will remain like that only. Okay. Sustained interference is obtained. Sustained interference is obtained. Okay, so what he did is he produced the two sources from single source only. So if suppose main source is this, okay, then he produced two sources from here only. So he kept one screen. On the screen he made two holes, which we are calling as double slit. Okay, so this is S1 and this is S2. So these are the sources which are produced from single source S. And then in front of that also he kept one screen on which we want to see the interference. Okay, so here it is. This is the screen. Now what? Now we all know that in the middle of this. Now remember that whatever we are going to see over here, the phase difference only depends on path difference. Path difference means the length of the path that waves are traveling. Okay. So see this point here. This is the middle point. So that means the wave which is traveling from S1 and wave which is traveling from S2 will be traveling the same distance. Okay. Because it's the middle part or middle point. So this wave is traveling here. Okay. Same way, another one is traveling from here. Both are traveling same distance. So when they are traveling same distance to reach this middle point, that means I can say path difference is 0. If path difference is 0 means phase difference also 0. That means we are going to get maximum intensity, constructive interference. Maximum intensity. Right? It's maximum intensity. So we call this as central maxima. Central maxima means where delta x is 0. And fortunately here it is on the center of the screen. Center of the two sources as well. Okay. So this is called central maximum. Because its intensity is maximum, we are calling it as central maximum. Correct? So here it is. But as you are going to move up or as you are going to move down, what is going to happen? Delta x is going to increase. Okay, it will increase. But is it possible that we are going to get again maximum intensities? Answer is yes, because it all depends on delta x and delta phi. If I am going to get again delta x equal to lambda, I will be getting maximum intensity. If I am going to get delta x equal to 2 lambda, again maximum intensity. 3 lambda, again maximum intensity. Right? So it's possible. As you are going to increase this path difference, we are going to get different intensities. Somewhere destructive interference, somewhere constructive interference. In between other intensities also, as we saw in the last question, I is the intensity resultant, 2I is the intensity, 3I is the intensity. All this will be there as you are moving around. Okay, but here we are going to search only the positions of destructive interference and constructive interference. Okay, now let's assume that here at this point, okay, we are searching another constructive interference, means maximum intensity. So suppose this point is y, this distance is y from central maxima substitution. Okay, let's join this again one more time. So from S1 and S2, waves will be reaching here. Okay, so let's make this as different color one, and this is also different. Right, so you made it. And also you connect this with the center of this one. Okay, but with center we'll connect little later. Now what we want, this point, let's say this point is P. What is the most important thing? As we said that phase difference depends on path difference. So path difference we have to calculate at point P. So what it is, this delta x at point P, what you'll be writing? Delta x at point P is actually equal to S2P minus S2. This delta x. Okay. Now, what is the separation between this S1 and S2? Standard notation for this one is D. Okay, small d. And separation between the sources and the screen, we take it as capital. Okay. Condition for YDSE, Young's double slit experiment, is capital D is very large as compared to small. That means these two sources are very close to each other. And as compared to this is negligible. So when this is negligible as compared to this, that means on this point, these two waves will be almost parallel. These two waves will be almost parallel. Okay. So since D is very large as compared to D, S2P is almost parallel to S1. So that means I have to just find out that how much larger this is, yes or no? S2P, how much is larger than S1? So how to do? If these two are parallel rays, then we drop a perpendicular from S1 onto S2. Okay, so I am dropping a perpendicular from here onto this. Okay, I dropped the perpendicular. Now what? After dropping perpendicular, let's put one name over here. Let's say M. Okay, now what we can say? I will say that S1P and MP are equal. S1P is exactly equal to M. Then what is delta X? The delta XP only will be S2M. Because S1P and MP are equal, S2P is what? S2M plus MP. Okay? S2P is what? S2M plus MP. Then delta X, which is S2P minus S1P. Okay? So what will happen? S2M and S1P are equal, we have written here. So delta X will come only what? S2M. So this is delta X. This we have to calculate. We wanted that only, and this is the value. Now how to calculate that? Very simple it is. Okay, what is that simple? What you'll do one more time now, one more line will take. And this line I am joining center point with this point. Okay, this I did. And I assuming that this is angle theta. Okay, this is angle theta. Now what I can say, I have already written over here S2P is parallel to S1. That means it will also be parallel to this middle line also, no? Obvious. And middle line means this point also we could give a name. Maybe we can give it as A. Okay. So S2P parallel to S1P is parallel to AB. Okay. So if this is angle theta, this angle, this line is making. So this line and this line also will be making the same angle with horizontal. Okay, correct? So with the horizontal, what angle this is making? Theta. Now this derivation actually is not important for you, but I'm just saying you that, okay? Because we want conclusion. But just see that. If this is theta, this is also theta. Correct? This line is making theta with horizontal. So this angle will be 90 minus theta. This is 90 minus theta. This is 90. So this is also theta. So from here I can calculate delta x very easily. From here, from this triangle. See this triangle. Okay. This triangle here. See this triangle. This one. Right. So theta, this is delta x and this is d. So I can write what? Sine theta equal to delta x by d. Because this is hypotenuse, this is opposite. Sine theta equal to delta x by d. Okay. Sine theta equal to delta x by d. So delta x is what? D sine. Okay. We got delta x is d sine. And one more thing is there. Now in this triangle you see. Okay. This is also right angle triangle. In this tan theta I can write as y by capital D. Okay. Tan theta equal to y by capital D. Right. Now since capital D is greater than small d, this theta is very small. So if theta is very small, I can write sine theta equal to tan theta. Okay. Since theta is very small, we can write sine theta equal to tan theta. So what are we getting here? We are getting sine theta value is delta x by d and tan theta value is y by d. So y equal to delta x capital D by small. This is very y equal to delta x capital D by small. Most important formula. Formula number 1, formula number 2, and if you remember this also fine. Delta x is d sine theta, tan theta equal to y by d. And that formula is y equal to delta x capital D by small. Okay. Now, if suppose that this was central maxima where path difference is 0. If this is going to be first maximum, this is called first maximum. Then here delta x will be what? Lambda. So what will be its position? That position will be given by this y equals. Okay, let's see. So y equal to delta x capital D by small d. So for first maximum, delta x equal to lambda. So y will be equal to lambda capital D by small. For second maxima, delta x will be 2 lambda. How I am getting? Because I know that for constructive interference, delta x should be equal to n lambda, where n is 1, 2, 3, 4 like that. Okay. So delta x is 2 lambda. So y value will be for second maximum 2 lambda capital D by small. Okay, can we get similarly for destructive interference positions also? Obviously, we can get it. For destructive interference then, what kind of path difference is required? Say lambda by 2, 3 lambda by 2, 5 lambda by 2, like that. And what should be the phase difference? Pi, 3 pi, 5 pi, like that. Okay. So for positions of minima, minima means destructive interference. Formula is same, y equal to delta x capital D by small d. What is delta x? I am writing is 2n minus 1 lambda by 2. And accordingly we will be. What is n here? N starts from 1. So 1 if you are keeping here, 2 into 1 minus 1 becoming as lambda by 2. So first the minima's position is y equal to lambda by 2 d by d. Second minima, y equal to 3 lambda by 2 d by d. So this way we can find the positions of maxima as well as minima. Okay. Now there is a concept which is called fringe width. Okay. Fringe width, which we represent with beta. What is fringe width actually? Fringe width is separation between two successive maxima or minima. Separation between two successive maxima or minima. Separation between two successive maxima or minima. Okay, so that means separation between first maxima and second maxima. Now what is the separation? You see, this minus this. So beta comes out to be lambda capital D by small. Lambda capital D by small. Important. Same way here also. 3 lambda by 2 d by d minus lambda by 2 d by d. Again lambda d by d. So this is called fringe width. Another thing is there which is called angular width. Angular width, which is represented in terms of theta. Tan theta we can say. Okay, so what is tan theta? Here we can see. So this is your first maximum. This is central maximum, and this is only theta, right? So between first maximum and second maximum, what we have? This will be beta. This will be equal to beta. So theta equal to beta by capital D. That is only angular width. Okay. So theta equal to beta by d. What's going to come? Beta value is this lambda d by d by d. So it will become lambda by. This is angular. Okay. Both the formulas we should remember. Clear? Okay. Now there is a question on this. But as I told you that when you are going to have YDSE, this kind of a pattern will be there throughout on the screen, so that you can see it whenever you want. There will be first maxima, second maxima, third maxima. Below also first maxima, second maxima, third maxima. Okay. Here it is. Okay. So what is happening here? If we say that this is central maxima, this is first maxima. So here also there will be first maxima. Whatever is there above the central maxima, same identical will be below also. That is only called sustained interference. Okay. Alright. Let's see what type of questions will be asked. Very simple questions are asked. Okay. See. So D equal to 5 lambda. That means separation between the sources is 5 lambda. Separation between sources and the screen is 10 D. What is intensity in front of one of the slit? Okay. So if here is S1 and here is S2, this is the screen. Okay. This is small d. This is capital D. Now he is saying that in front of this, here, suppose this point is P. Okay, what is intensity in front of one of the slit? Here is central maxima, we know, here is delta x0. Here what is the intensity? So that means again we have to calculate path difference only. Correct or not? Path difference. What is path difference? We already know delta x equal to d sine theta. We know that. We calculated in the previous case. Delta x equal to d sine. And tan theta equal to y by d. Now what is y here? This is what? D by d. He said no in front of one of the slit. So y equal to d by 2. That means this is d by 2d. And since we are doing Young's double slit experiment, so I can write sine theta and tan theta are equal. Okay, so in place of this I can write sine theta. Sine theta is what? Delta x by 2 equal to d by 2. So delta x value is coming d square by 2. Now let's put the value and see what it is. What is small d? Small d is 5 lambda. So this will become 25 lambda square. by 2 into 10d. Oh. So instead of putting here right now, let's put it as d square. Okay, and this capital D is 10d, 10 small d. So 1d and 1d is cancelled. So d by 10. Okay, what is d? D is 5 lambda. 5 lambda by 10. That means it's lambda by 2. That is delta x. So delta x is lambda by 2. So delta phi is what? What is delta phi? Delta phi is pi. How? We know delta phi equal to 2 pi by lambda into delta x. Oh, it will not be pi, right? We'll see. Check. 2 pi by lambda into lambda by 2. Pi only, correct? Correct. Delta phi is pi. Now, how to get intensity? Is asking intensity. Intensity also similar. We can find it very easily. What it is, if this is I and this is also I, then at this point, what will be resultant intensity? Don't we know that? We know that IR will be equal to 4I cos square pi by 2. This only. Correct only? What we are going to get there? Minimum 0, because when you are going to keep pi here, pi by 2 means 90, cos 90, 0. So resultant intensity is going to come 0. That means at this point we have minimum intensity. This is minimum intensity, or anyhow we are getting delta phi is pi. That is the condition of destructive interference. Okay. Alright, let's see next one. In Young's double slit experiment, I for the path difference delta x is I naught, where delta x is lambda. Delta x is lambda means he is talking about maximum intensity. In the previous case, you saw that delta x was lambda by 2. We got minimum intensity. Here, delta x is lambda. We are going to get maximum intensity. So, maximum intensity is how much? I naught, yes. What will be I delta x dash if delta x is delta x dash is lambda by 2? So, we have to calculate. Okay, see. So, first thing is I maximum is I naught. Delta x dash is lambda by 3. So, what I will do is, first of all, I will calculate the corresponding phase difference. Phase difference delta phi is 2 pi by lambda into delta x. That is 2 pi by lambda into lambda by 3. Lambda cancel. 2 pi by 3 is coming as phase difference. Is it okay? So, I at delta x dash will be equal to I max into cos squared pi by 2. This is what we know. Or, okay, leave it. No or. Here on I naught cos square. In place of 5, what we can write? 2 pi by 3. 2 pi by 3 by 2. So 2 gets cancelled. It's pi by 3. Pi by 3 means it's 60. So cos of 60 square. Cos of 60 is 1 by 2. 1 by 2 square means 1 by 4. So our intensity is I naught by 4. Okay. Next. In Young's double slit experiment, small d is equal to 2 mm, capital D equal to 2 meter, lambda equal to 500 nanometer. If intensity of two slits is I naught and 9 I naught, so different intensities are here. Find intensity at y equal to 1 by 6 m. So main thing is again, what we want is what is the phase difference at that particular point, so that we can calculate the resultant intensity. Okay. So all right. Y value is given. Okay, now y value actually is what? Say delta x capital D by small. Delta x capital D by small d. So from here delta x we will calculate. Okay, so y is 1 by 6 mm and all the things are given in meter. Okay, so let's put everything in meter or everything in millimeter. Okay, so 1 by 6 of a millimeter. So 1 by 6 into 10 to the power minus 3. Delta x capital D is 2 meter and small d is 2 2 into 10 to the power minus 3. Okay, and this 2 and 2 gets cancelled here. So delta x is coming 1 by 6 into 10 to the power minus 6. This is delta x. Right, now delta phi you calculate. Delta phi is 2 pi by lambda into delta x. So 2 pi, this is 500 nanometer, that means 5 into 10 to the power minus 7 meter into delta x. How much is this? 10 to the power minus 6 by 6. Right, so what's coming from here? This is 10 to the power minus 7, it will go up here. 2 pi by 5 into 10 by 6. So this is 2 and this is 3. So 2 pi by 3 is coming as delta. So now no problem. No problem. Now resultant intensity will write. So what is resultant intensity? I1 plus I2 plus 2 root over I1 into I2 into cos phi. We cannot use 4 I naught cos square phi by 2 here because both intensities are different. So we have to use this formula only. So I naught plus 9 I naught plus 2 root over I naught into 9 I naught into cos 2 pi by 3. Cos 2 pi by 3 means what? 120 degrees. Cos 120 degree means is minus 1 by 2. So minus 1 by 2. This gets cancelled. So this is 10 I naught and this is minus 3 I naught. 10 I naught minus 3 I naught means 7 I naught will be our answer. Okay, so here it is. Then what is position of 8th bright fringe? Okay, simple it is. Now position when we are talking, that means delta x capital D by small d. 8th bright fringe. Central maxima is 0. Central maxima is called 0th bright fringe because delta x is 0 there. 8th bright fringe means their path difference should be 8 lambda. Delta x should be 8 lambda. So I am writing 8 lambda. Capital D by small d. That is the position of 8th bright fringe. Then find difference between 5th bright fringe. So 5th bright fringe 5 lambda d by 2 and second dark fringe. Okay, fine. So y for 5th bright fringe is 5 lambda capital D by 2 and y for second dark fringe. For dark fringe what we said, y equal to 2n minus 1 lambda by 2 is the path difference. Okay, 2n minus 1 lambda by 2 d by 2. So what is n here? 2. So 2 into 2 minus 1, that is 3. So 3 lambda by 2 by 2. Now what is the path what is the difference between the two? This is 3 by 2 and this is 5. So what is the difference? 5 by 2, right? 5 lambda d by d minus 3 lambda by 2 d by 2. So this is 5 minus 1.5, 3.5. 7 by 2 lambda d by d will be the difference between the two. Okay, 5 minus 3 by 2, that's it. Then fringe width, if lambda is double, d is triple and d is half. Okay, what is fringe width? Fringe width is lambda capital D by small. So beta dash says lambda is doubled. Okay, 2 lambda. D is tripled. Okay, 3d and small d is half. So it's d by 2. So 2 into 3, 6 into 2, 12. So it is 12 lambda d by 2. It becomes 12 times. Beta dash is 12 beta. Okay. What this is now? In YDSE for lambda 1 equal to 3000 angstrom, 40 fringes are observed. On the screen, 40 fringes are observed. Then for lambda 2 equal to 200 angstrom, how many fringes are formed on the screen? Okay, what to do in this case? Now we know that If we are saying only 40 are observed or 20 are observed or 30 are observed, that means that much space is there on the screen. Okay, and every fringe width is beta. Its fringe width is beta. So 40 fringe width space is there. Okay, so in that 40 fringe width space, how many fringes of this will accommodate? So I will say that depending on how much is the string size, I will say that n1 beta 1. That means number of fringes of one type of wavelength must be equal to n2 beta. Correct only, no? Because each fringe width is beta. So in this one 100 are accommodated. So in this one, how many are accommodated? So given to us 40, beta is what? Lambda d by d. Lambda is what? 3000. Let it be in angstrom on capital D by. Here N2 we are finding lambda is 200 into capital D by small d because setup is not changed. D by t cancelled. 40 5 ja, and this is how much is how many are coming? 600. So N2 is 600. 600 fringes will be there of wavelength 200. Okay. All right. Now, one more question we will see. Normally, it will be asked from you that how many maximum intensities we are going to get on the screen. Okay. How many maximum intensities will be obtaining on a screen for a particular data will be given to us. Okay. How many maximum intensities will be coming on the screen. So, how to do it? See, we have this formula. Delta x equal to d sine theta or sine theta equal to delta x by d. Okay. What to do then? This formula sine theta equal to delta x by d, and delta x is actually n lambda if I am talking about maximum intensities. Okay, now what is the maximum possible value of sine theta? 1. Keep 1 for n lambda. So what is n value? N value comes out to be d by lambda. Okay, so these many number of maximum intensities are possible above the central maximum. Same way below the central maximum also. Okay, below also same one, above also same one. So what are the total number of maximas we are going to get on the screen? It will be 2n plus 1. This is above, same is below, and then central maxima is also there. So total number of maximas that we are going to obtain will be how much? 2n plus 1. But remember here you have to take, if suppose this is coming in fraction, so you have to take whole number multiple on. You are not going to take fraction. Understood that? So these are the total number of maximum intensities that we are going to obtain on screen. Okay. Now what is next? Next is little bit of idea about wavefront. What is wavefront? Wavefront was the idea given by Huygens to us. Okay, and according to it, waves actually travel in the form of wavefront. Okay, waves travel in the form of wavefronts. Right. Then he said there are 3 types of wavefronts. 3 types of wavefronts are there. Okay, one spherical, cylindrical, and plane. Now it all depends on what type of source it is. If suppose we are talking about spherical wavefront, then definitely the source for producing waves is a point source. It is a point source. Okay. So what is happening if it's a point source? Waves are going in all directions because it's a source of light. Light goes in all the directions. And how light is moving? In the form of waves, we know. Okay. So wavefront basically is what? spherical wavefront when I am saying, its meaning is all the particles on this will be in same phase. Okay, what is wavefront? All particles vibrating on a wavefront are in same phase. Okay, are in same phase. Now, what is the same phase meaning? It means first of all is if this is a source, then we know that if this is a sphere, then all the points are at same distance from it because this is radius actually. Correct. Now, if I am going to make one wave over it like this, okay, so this particular source will be producing these waves. They will be of same wavelength. Okay, so if they are of the same wavelength, then obviously this part here will be in same phase, and all the particles here vibrating will be in same phase, and they will be with a constant phase difference from here. If this is at 0, its phase difference, if its phase I consider 0, then its phase has to be 2 pi because the difference is 1 lambda. So you can have even half lambda difference, or even less than lambda by 4, or maybe even less than. I can make many wavefronts on that one, because wavefront basically is all particles vibrating on a wavefront should be in same phase. After this, one more I can make. Correct. But all the particles on this should be in same phase. That is important. Correct. Same way, when it will be cylindrical wavefront, when we are going to have line source. Line source means what? Line source means it's like this. So in this one, how light will be going? Light will be going perpendicular, like this. So what type of wavefront here will be the cylindrical wavefront, like this. Okay, now here I can make one wave, let's say half a wave on this side also. So this, all the particles are in same phase. When we will have plane wavefront, when the source is at infinite, very far from us, then we consider that the wavefronts will be plane wavefronts. When source is at infinite. Okay, remember. And second important point is, this wave basically is what? Energy only, no? So the point, or the time rather, time taken by a wave to move from one wavefront to other wavefront at every point will be constant. Okay, time taken by wave, time taken by wave to move from one wavefront to other is constant at every point. That means from here to here, how much time energy is taking, same time it will take from here to here, same will be taken from here to here, same will be taken from here. That is what I am trying to say. Okay, remember that. That's important point. Now, what type of questions we ask in this one also? Okay, in this also we have certain questions. Okay, so let's see what questions we can do. Just erase this one. Diffraction may not be possible to start today. Okay, so we'll at least finish the interference. Okay. So what will happen is, they will ask us that if suppose that we are going to keep optical instruments in front of the plane wavefront, then what will become the shape? Okay, plane wavefront means how to show. One more thing. When we talk about the waves, okay, waves, they are traveling in straight line. Okay, so these waves will always be perpendicular to the wavefront. Okay, this will be perpendicular because this is radial, and this wavefront, if I am going to make a tangent, it will show you that these are perpendicular. So propagation of light is always perpendicular to wave. Okay. Alright. So now what I am going to do, I am going to make plane wavefront, and plane wavefront, this is plane wavefront. Plane wavefront means where is the source? In fact, this is our plane wavefront. Not plane wavefront, I am just making actually light. Light is coming like this. These are rays of light. Rays of light means is energy. Energy is coming like this. Now how will be the wavefront? Plane. Like this. This plane wave. Okay. This is plane wavefront. Now what we want is, we want to keep one optical instrument in front of this one. And we want to see how is going to be the shape of the wavefront. Now suppose that I am going to keep one concave mirror. What will happen? These are rays coming from infinity. We know that they will converge at focus. Yeah? Yes or no? Yeah. So only these two I am making over here. Okay. So it will be coming in this way, and this will be coming in this way. Okay. So how will be the wavefront? Wavefront will be like this. Okay. Consider this is the source now. Though it is actually here convergence is there. But consider this as the source. Now from here, how will be the wavefront you will be making? Spherical. Because this is point source now. No? From point source, what type of wavefronts are possible? Spherical. So it will come like this. These are the shape of wavefronts. Exactly similar in length also. Now you understood how to make it. Correct or not? You must have understood now how to make it. So this thing again I have to make one more time. Right? This is here. Okay. Now what? We have what? Lens. Convex lens. Now what's going to happen? This is also going to converge. So converge means take top two, this one and this one. Now what do you say? Consider this is the source. Now how will be the wavefront produced by this will be? Spherical again. So here. Correct. Prism is there. Prism is not converging or diverging. It's just deviating. So a plane wavefront is coming. It will remain plane only, but only that the direction will change. This is prism. Okay. So one plane wavefront we are making from this side. Okay. It's like this. What will happen in prism's case? This is incident rays. This side will be emergent rays. So that will be like this. Okay, like this it will become. So if here our wavefront is like this, here it will become like this. That only is the difference. Okay, so this way wavefront's shape is changing, wavefront's type is changing. Okay, because here is plane wavefront, here it became spherical wave. Okay, so today's class I am finishing here. I completed YDSE interference. Okay, in tomorrow's class we will do the remaining part, that is diffraction and polarization, along with electromagnetic waves. We will finish. Okay, so scan the code. Here it is for you. Scan it so that you can have the notes. Okay, students, then see you tomorrow. Bye bye.